Today's lesson is going to be changes in state of matter. This is from topic 2, lesson 2. So we still have our same essential question. What causes matter to change from one state to another? And you have some pictures here that will help you to remember what we've been talking about. Last time we talked about the different states of matter, including plasma a little bit. This is talking about our convection, conduction, and radiation heat, which we'll be talking a little bit about in future lessons. This is our gas lesson, which is the next lesson, and Charles' law is part of the gas lesson as well. Those pictures are to kind of trigger what the unit is about. Here are our science standards. So these are the ones you see on your report card. Can you ask questions and define problems? Can you develop and use models? Plan and carry out investigations, analyze and interpret data, use mathematical and computational thinking, construct, explain, and design solutions, and obtain, evaluate, and communicate information. So all of your assignments are designed to hit these standards. And this is the substandard for today's lesson. Develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. So that's what we'll be talking about. Here are our objectives. We'll be doing these at the end, so you just kind of keep them in mind. I'm going to move quickly through the objectives here and catch them at the end. Okay, what do thermal energy and temperature have to do with changes in the state of matter? Remember, thermal energy and temperature are not exactly the same thing. So changes in the state of matter will all involve a change in thermal energy and the temperature of the substance. But before we can explain the difference between the thermal energy and temperature, we have to know about potential energy and kinetic energy. You may have heard these terms in the past. Have you ever heard someone say to you, you have a lot of potential? What are they really saying to you? Maybe a teacher said it to you, maybe a coach, maybe a mom or a dad or a grandma or a grandpa or an aunt and an uncle, maybe a cousin. What are they really saying? You have a lot of potential. Well, they are saying that you have the ability to become something greater. You have something inside of you that can make you something greater. And you all have something inside of you that can make you into the greatest you can be, right? It's all there. It's all potential inside of you. So potential energy then is stored energy that can become something greater. I'm going to draw a rough picture here of a roller coaster. Okay, here's my roller coaster car. It's going up the hill. So the potential energy is right at the top of the hill. That coaster has the potential to go really, 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 really fast when it goes down the hill. So that's stored energy. It's just waiting to release that energy to go down that hill super fast. So I'll put myself in there because I like roller coasters. And here I am. I'm usually not smiling. I'm usually screaming, but that's okay. And my hair is probably standing on end. So anyways, there's potential energy. What is kinetic energy? Well, that is energy already in motion. So as soon as I start to go down this hill, I am releasing kinetic energy. My roller coaster is now in motion. That stored energy is being used. Try to put myself with an I'm screaming. Okay. Anyways, I diverse. Can't really tell that's me screaming. But potential energy is energy about to happen. Kinetic energy is energy that is happening. It's another way of looking at it. Okay. We'll talk about that more when we get to motion and force in a few weeks. What do thermal energy and temperature have to do with the change in the state of matter? Well, thermal energy is the total kinetic and potential of all the particles in an object or substance. So it's all the energy. It's energy moving around plus the energy that's stored up and ready to move around. Okay? That's thermal energy. So it's all the energy that's stored and all the energy that's already in motion in the particles. I just said that. You can increase the thermal energy of a substance by heating it. Okay? And when you apply heat, you are transferring energy from the heat to the substance. And that makes sense. The heat on your flame here, this open flame, is being transferred to heat inside of the pot, inside of the water. If you transfer enough heat, the substance can change its state of matter. It can melt or it can turn into a gas. In our case, with this liquid here, it will turn into a gas if you keep heating it. If you have a solid, that will get melted if you put heat to it, right? Think about a chocolate candy bar, right? Okay, next, let's talk about temperature. That is the measure of the average kinetic energy of the particles in a substance, not including potential energy. So if you think about what's an average, so if I added 1 plus 2 plus 3, the average of 1, 2, and 3 is, well, the total is 6. The average is, add up the numbers and divide by the number of numbers, 1, 2, 3 numbers. So it's 6 divided by 3. The average of those numbers is 2. So you're adding up the temperature, you're adding up the thermal and the temperature and potential and kinetic energies, and you are finding the average. So it's a little bit different. The faster the particles are moving, the greater their kinetic energy and the higher the temperature of the substance. So think about that boiling water. The longer you boil it, the quicker the bubbles go, right? Boop, 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 boop. They go really, really quick. Temperature is measured using a thermometer. That should be a no-brainer. I'm sure you all know what a thermometer is. You can make particles speed up by heating a substance so that its thermal energy increases and its particles move faster. You can make particles slow down by cooling a substance so that its thermal energy decreases and its particles slow down. You can think of this in terms of if you jump in an ice cold water, like a pond or something, or Lake Michigan in the freezing cold, when it's like -5 below zero. Your body will start to slow down in the water. Your muscles are going to start to contract and freeze up, and you're not going to be able to move very fast. Why? Because you're cooling down and your thermal energy is decreasing, and the particles inside of you are starting to slow down and get very slow. Okay, thermal energy is the total kinetic and potential energy of all the particles in an object substance. So I'm just showing you some pictures here. So here's more thermal energy on the left here. Here's less thermal energy. Notice the particles are moving slower. Here it is in terms of temperature. Here you have a temperature just slightly above zero, and this is in Celsius. They're moving a little bit, raise the temperature, they're moving a little bit more, and raise the temperature a lot, and they're moving a little bit more. Okay, hopefully that's a good picture of it for you. What is changing from a solid to a liquid called? Well, melting. I bet you knew that. Melting is the change in state from a solid to a liquid. Ever watch The Wizard of Oz and they pour that hot boiling water on the witch and she says, I'm melting, I'm melting. Melting is changing from a solid to a liquid. So melting involves an increase in thermal energy. You have to increase the thermal energy for the melting to start. Particles of a liquid have more thermal energy than particles of the same substance in solid form. So this solid chocolate does not have as much thermal energy as this liquid chocolate. Which has more thermal energy? A solid, I just told you, a solid chocolate bar or a melted chocolate bar. I hope you said melted. A melted chocolate bar has more thermal energy than a solid chocolate bar. What is the process of melting in a crystalline solid? Well, a crystalline solids always melt at a specific temperature called its melting point. What happens when an ice cube is taken out of the freezer? You can see what's happening. It starts to melt. Energy flows from the environment around it into the ice, and it makes the water molecules vibrate faster. The faster vibrating particles raise the temperature of the ice cube. As the ice cubes At the ice cube's melting point, the particles vibrate so fast that they break free from their fixed positions. What happens then? When the ice reaches its melting point, in this case 0 degrees Celsius, 32 degrees Fahrenheit, its temperature stops increasing, and any added energy continues to change the arrangement of the water molecules from crystals into solid water. That's the key. So once it reaches that melting point, the temperature stops increasing, and the added energy now is going to change it to a different state. In our case, a solid to a liquid. Does the melting point of a substance change? Well, the melting point of a substance is always the same. It doesn't matter how much of a substance you have. It doesn't matter how much ice you have. It still always melts at the same temperature. Scientists use melting point to distinguish between look-alike substances. So for example, don't these substances look alike? They do pretty much. Silver and iron are both shiny metals that look alike. However, silver has a melting point of 961.8 degrees Celsius, and iron has a melting point of 1,538 degrees Celsius. So if you try to melt one of them and it melts sooner than the other, if you can get it to that high of a temperature, you will know which one is silver and which one is iron. So silver is on the left and iron is on the right. Did you know that? Did you guess that? Good. What is changing from a liquid to a solid called? Now we're going the other direction. What do you call it when you change from a liquid back to a solid? Did you say freezing? I hope so. Freezing, the change in state from a liquid to a solid. Here's your your water getting cold and freezing in fast motion. Changing back to a solid. Freezing always involves a decrease in thermal energy. Just the opposite, right? Particles of a solid have less thermal energy than particles of the same substance in liquid form. This water has more thermal energy than the ice. At 0 degrees Celsius, water molecules move more slowly and become fixed in place as the liquid water turns into a solid ice. Notice how that's also the melting point. So the melting point and the freezing point are the exact same point. That's the point where the substance is about to change from one state to the other. Substances do not have to feel cold to the touch in order to freeze. There is actually a special wax that freezes at 145 degrees Fahrenheit. Does the freezing point of a substance change? What do you think? No, the freezing point of a substance is always the same. It doesn't matter how much of a substance you have, it will always freeze at the same temperature. You could have a whole pond of water, or you could have a glass of water, and it will freeze at the same temperature. At a liquid's freezing point, its particles are moving so slowly, they begin to take on a fixed position. An object's melting point, like I said, is the same as its freezing point. Gaining or losing energy. Okay, when an object melts, is it gaining or losing energy? When an object melts, what do you think? Gaining or losing energy? It is gaining energy. Okay, the next one. When an object freezes, is it gaining or losing energy? Losing energy. Hopefully you're right on that. What is changing from a liquid to a gas called? Vaporization. That's the change in state from a liquid to a gas. Vaporization involves an increase in thermal energy. The particles in the liquid gain enough energy to move independently and away from each other. They break free. What are the two types of vaporization? There's two types. There's boiling. That's the water molecules breaking free of the liquid and forming a gas. Vaporization that takes place below and at the surface of a liquid is called boiling. You'll notice that those water bubbles will boil from the bottom to the top. Bubbles form, rise, and eventually break through the surface of the liquid. Boiling points are always the same for a substance, no matter how much of the substance you have. The second type of vaporization is called evaporation. Vaporization that takes place only on the surface of a liquid is called evaporation. It doesn't take place in the bottom and the middle of the liquid, only on the surface. You know that after a rain, eventually the water in a puddle disappears, or the water on that little leaf there. The puddle of water is said to vaporize. The temperature in the water has not reached its boiling point, and only the particles on the surface have enough energy to turn into a gas. Energy is transferred from the sun's radiation and the air. And evaporation occurs at all temperatures, while boiling occurs only at one temperature. That's a key. Evaporation occurs at all temperatures, while boiling occurs only at one temperature. Worth repeating. Okay, here's evaporation and boiling. Oops, I want to go back. Escape, escape. So here's an example of evaporation versus boiling. Evaporation, it's only the liquid particles on the top. Boiling, there's a bunch of liquid particles and bubbles in the whole liquid. Okay, that's a picture of that. How does pressure affect vaporization? Pressure is a force when you push on something. So think about pressure being a force. Like if somebody sits on you, they're putting a lot of pressure on you. Hopefully you don't ever let somebody sit on you, but pressure depends on the force you apply in the area over which you apply the force. So here's a formula. We're going to actually be doing a worksheet on calculating force and area and pressure. So pressure is equal to force divided by area. So what that kind of means is, let me just draw a square here. So pressure is going to be the amount of force you're applying to a certain area. So if you're applying the same force to two different areas, let's say, if you're applying the force to this smaller area, the pressure is going to be greater than if you're extending the force over this larger area. Then your pressure is going to be less because you have a bigger area. So that's what the formula is kind of showing you there. Gas particles constantly collide with one another and with nearby surfaces. When the gas particles hit other surfaces, this applies a pressure to those surfaces. So if you think about it, if you have a bunch of, let me just put a little things here. If you have a bunch of little particles, let's say inside of a balloon, for example. There's your balloon. Gas particles. So those gas particles are applying a pressure to the outside of the balloon as they collide and bump each other. They're also hitting the edges of the balloon. So they're applying a pressure to it. Okay. If particles collide more often on surface, the pressure is greater. The air around you, a gas, applies a pressure to you, too, constantly. So this pressure, if you think about it, the air actually has weight, and it is actually pushing down upon you. I'm ready for the black bar to go away. There, this pressure is called atmospheric pressure. So it's the pressure from the atmosphere. It's the amount of pressure from the air pushing down on you. How does pressure affect vaporization? Well, let's think about this. Okay, here's a picture. Look at how few atoms are pressing down on the guy at the top of the mountain. See, there's less there's less molecules, less pressure. Look at all the atoms pressing down on the guy at the bottom of the mountain. See how they're all a lot closer together? Plus there's a lot more above him than this guy has above him. So you have less atoms of air, that equals less pressure. And more atoms of air is going to equal more pressure. I don't know why my animations are off there. Atmospheric pressure affects the boiling point of a liquid. So let's take a look here. So this liquid here, this is a mountain, supposed to be a mountain, going up the mountain. This is a lower boiling point. And this is the pressure pushing down on this is the air pressure pushing down on the pot here. So if you notice, we're higher up on the mountain. This brown spot is the mountain. So the amount of air pressing down on the boiling water is going to be less than if you're at the bottom of the mountain. So you're going to have a lower boiling point. That means the bubbles aren't going to have to overcome as much force pressing down on them to escape the pot. They don't have as much force. So high altitude equals less air molecule pressure, which equals less force needed to overcome the atmospheric pressure. So you don't have to have as much of a push to get out of the pot at the top of the mountain than you do at the bottom, which is what we'll look at now. Here's the pot at the bottom of the mountain. Now look at all the difference. Look how much more molecules of air are pressing down on the pot at the bottom. It's because it's lower altitude. So the force pushing down on the water is way more than the force pushing down from the top of the mountain on the water. So what do you think about the boiling point of this water? Is it going to be more or less? Right, it's going to be higher because these bubbles have to overcome more force pushing down on them to escape the pot. So low altitude equals more air molecules pressure. So that equals more force needed to overcome the atmospheric pressure. So you're going to have to get the water a little bit hotter at the bottom of the mountain than you do at the top of the mountain. So you have a higher boiling point at the bottom of the mountain. I encourage you to go back and look at these slides again. How does pressure affect vaporization again? The greater the atmospheric pressure, right, the more molecules above you, the higher the boiling point needs to be. Atmospheric pressure is pushing down on the pot of boiling water. So the air above the pot is exerting a pressure on the pot of water and on just about anything else you can think of. The higher you go, the less air pressure there is. There's just less air. It's less dense. Eventually in space, you don't really have the air at all pressing on you. You just float off into space. As water is heated, the pressure inside the water increases, creating an upward force. Okay, now we got an upward force and a downward force. The upward force, the yellow arrows here, has to overcome the downward force from the air pressure. When the pressure inside the water equals the pressure from the atmosphere pushing down on the pot, the water begins to boil. Has to escape, has to get more pressure to escape. At higher altitudes, liquids will boil at a slightly lower temperature. Why? Well, because the liquid has less atmospheric pressure pushing down on it and not as much heat is needed for the molecules to break free from the pot. Be sure to understand these concepts. Definitely go back and review these slides. At sea level, water boils at 100 degrees Celsius. And in higher altitudes, it boils at only 95 degrees Celsius. So just a slight difference, but it will boil quicker with a less temperature higher up. So if you live in the mountains, you don't have to boil your water as long. Okay, let's take a look at it from this visual. I don't know, my animations are doing weird things. Which pot requires more thermal energy to, oh, you know what? I have to go back because that was just one slide. Let me go back to slide 24 here. There, let's take a look at this. So, at sea level, water is boiling at 100 degrees Celsius, which is 212 degrees Fahrenheit. I'm trying to get that black bar to go away. Come on, black bar, go away. Anyways, and then if you go up higher in the mountain, at 6,000 feet, water is going to boil at 200 degrees Fahrenheit or 93 degrees Celsius. See how it's getting less? And if you go to the top of the mountain at 10,000, well, not the top, 10, yeah, it is the top, 10,000 feet, the water will boil at 90 degrees Celsius or 194 degrees Fahrenheit. The temperature is decreasing the amount that's required to boil the water. If you go way up in an airplane and you were to boil water at 20,000 feet, the water would boil at about 175 degrees Fahrenheit or 79 degrees Celsius. Look at the difference. There's a big difference from 79 to 100. And that's because you're so high up. Okay, hopefully that makes sense. Now we'll go to the next slide. Okay. Which pot requires more thermal energy to change into a gas? Okay, let's see if we can answer the quiz. Okay, this one or that one? Which one is going to require more thermal energy to change into a gas? Did you say the one with more molecules above it? Then you are correct. Greater air pressure equals more force or heat needed to overcome that air pressure and escape the pot. Okay, let's look at this pot versus this pot. Which pot is going to require more thermal energy to change into a gas? I hope you said the one with the molecules closer together, right? They're putting more pressure on the pot. Doesn't matter about the altitude in this case. This is a density question, right? So it would be the one with more molecules concentrated in a small area. Gas particles closer together, indicating they are under more pressure, more force needed to overcome air pressure and escape the pot. So this second example is not an example of altitude. This is an example of space. So we're going to learn this in the next lesson, but gas can be compressed into smaller areas. And that if you compress the gas, you put more pressure on the gas, you're crunching up the molecules like this picture here. You're crunching the molecules up more. You're putting them under more pressure. So this is a picture of more pressure than this one. This is a bigger area, less pressure. Okay, continuing on. Can you answer these questions? Will a liquid turn into a gas if the pressure above the liquid is increased and no thermal energy is added to the liquid? So you're not adding any more heat, no more thermal energy, but will a liquid turn into a gas if the pressure is increased? What do you think? No, the liquid will require additional thermal energy to boil or evaporate. Next question. Water has a lower boiling point in higher elevations. We just talked about that. What can you conclude about the atmospheric pressure in higher elevations? Is the pressure more or is it less? The atmospheric pressure at higher elevations is less. It's lower than at sea level. Less pressure lowers the boiling point of water. Number 3, a sample of liquid is under high pressure and another sample of the same liquid is under low pressure. Maybe one's being squeezed into a smaller area than the other. Which requires more thermal energy to change from a liquid to a gas? The one under low pressure or the one under high pressure? Did you say high pressure? Good. The sample under high pressure requires more thermal energy to change it from a liquid to a gas. It has more pressure to overcome to escape the pot. What is the reverse of vaporization? You might be able to tell from the picture. Condensation is the change in state from a gas back into a liquid. Condensation is the reverse of vaporization. When particles of a gas lose enough thermal energy, so the key word here is lose the thermal energy, they change back to a liquid. Water vapor is a colorless gas that you cannot see. You cannot see water vapor. When warm water vapor in your breath reaches a cold window, the water vapor condenses into liquid droplets. This is a gas, the water vapor from your breath, turning into a liquid, water droplets on the window. Fog is also water vapor in the air that condenses into tiny liquid drops. And you can always think when it's foggy out, you walk through the fog outside, you're going to get your hair more kind of moist and wet. You're going to feel like it's wet. Water vapor is not steam. That's something different, okay? It's not steam above a boiling water. Water, 2 T's, should be 1. Water vapor is not steam above boiling water or fog. Steam and fog are tiny droplets of liquid water suspended in air. I don't know what's up with my animations today. What is changing from a solid to a gas called? Did you ever hear of that? Can you change from a solid to a gas? Has anybody ever done that? Don't you normally go from solid to liquid and then from liquid to gas? There is a way of changing from a solid to a gas and skipping the liquid phase. It is called sublimation. I don't know what, that clears, I gotta clear that circle. Sublimation occurs when the surface particles of a solid gain enough energy that they form a gas and do not even pass through the liquid state as they form the gas. That's called sublimation. So dry ice is an example of sublimation. Dry ice is solid carbon dioxide. At ordinary atmospheric pressures, which we have normally on the Earth, carbon dioxide cannot exist as a liquid. So instead of melting, solid carbon dioxide changes directly into a gas. Very interesting. There's an example. That's solid carbon dioxide changing directly into a gas. As it sublimes, the carbon dioxide absorbs thermal energy from its surroundings, much like an ice cube absorbs the thermal energy from its surroundings. And then ice cubes, however, melt. They turn to liquid first. Carbon dioxide will turn to a gas. Dry ice can be used to keep materials cold or as a fog machine in movies where the dry ice cools the nearby water vapor, which condenses, forming fog. Okay, we are done with our lesson. Here are your questions I said I would go over. So you're going to have to define potential energy and kinetic energy. That would have been the first slide or two. Explain the difference between thermal energy and temperature. Remember, one is an average, one is a total of the kinetic and potential energies. Which one is which? Define melting and explain what happens to the thermal energy and particles when a solid melts. What happens to the thermal energy when a solid melts? Think about that. Explain the process of melting in a crystalline solid. And all of these are on the slides. You don't have to look in your book, but you could. You don't have to look on the internet. Please don't use Mr. Internet because then you get a lot of big words and you're like not sure what you're understanding. If you look back on the slides, all the information is in the slides. Next, define freezing and explain what happens to the thermal energy and particles when a liquid freezes. Explain why an object's melting point is the same as its freezing point. Think about that one a little bit. Define vaporization and explain what happens to the thermal energy and particles when a liquid turns into a gas. Next page, define the 2 types of vaporization and list 2 differences between each type. Now, these questions seem hard, but they're really not. All your answers are on the slides. Define pressure and atmospheric pressure. Explain how pressure affects vaporization, right? Boiling and evaporation, and why pressure affects vaporization. Define condensation and explain what happens to the thermal energy and particles when a gas turns into a liquid. And finally, define sublimation and give an example of a substance that sublimes. That one should be easy. That should be the last slide that we just looked at. Which substance sublimes? Yes, solid carbon dioxide. Good. I believe that is the last page. So I will come back and have a good day. See you next time. Bye.